Concrete is naturally brittle. Typical stresses like impact, fatigue, and loading lead to cracking and eventual failure. Adding reinforcement to the concrete helps to absorb these stresses and to limit the formation of cracks, increasing the load-bearing capacity and ductility of the concrete structure.
Concrete is around us everywhere. If you think about it, our whole civilization is made of concrete. Before we talk about why civil engineers use steel in reinforced concrete, let's talk about concrete in general and what is it made of. Concrete is made of coarse aggregates like gravel, fine aggregates like sand, cement, and water. We can definitely add other ingredients to concrete to serve some specific purposes, but we will talk about that in the future videos. The impressive thing about concrete is that it is very strong in compression. Regular or unreinforced concrete has a compressive strength of around 30 megapascals. But what does that even mean? It means that you can stack 5 people on the top of each other over a very small area of 1 centimeter square of concrete, and it will be fine. On the other hand, concrete is extremely weak in tension. Usually the tensile strength of concrete is around 10% of its compressive strength. This means if you have a square bar of 1 centimeter by 1 centimeter, then you can barely handle the weight of 3 raccoons. You are asking how much a raccoon weighs. A big raccoon will weigh around 10 kilograms. The limitation of concrete tensile strength led ancient builders and even Gothic cathedral builders to construct arches and domes that are almost void of any tension regions. In other words, they tried to build the structures to be all in compression. If we have a simply supported beam made of concrete and it is uniformly loaded, then we will actually have compression on the top and tension on the bottom. Now, for compression, we know that concrete is great and can take the load. However, it sucks in tension, so it will fail there. So what do we do? Engineers solved this problem by introducing or reinforcing concrete with another material that is strong in tension, mainly in the tensile region. Actually, it wasn't engineers who thought of that. The brilliant idea was discovered by the French gardener Joseph Monnier in the mid-19th century, who was not satisfied with the materials available for making flower pots. Clay was easily broken. So what did he do? He embedded iron into the clay flower pots to reinforce them to make them stronger. And guess what? This guy patented the idea and even built the first ever iron reinforced concrete bridge. Nowadays, we use steel instead of just iron in our buildings and bridges. Remember, steel is an alloy of iron and carbon and other ingredients, which make steel superior to the metal iron. As you can conclude from the discussion, steel is extremely strong in tension and even in compression. To put it into perspective, remember the square 1 centimeter by 1 centimeter rebar. If it is made of steel of a tensile strength of 420 megapascals, then you can let around 400 raccoons hang to it and it will be fine. Now, you can ask, titanium is even stronger than steel, so why not use titanium? I think the reason should be obvious. Titanium is much more expensive than steel. But actually the main reason we use a steel alloy is due to its special coefficient of thermal expansion. When the temperature rises, the concrete and steel will expand. If each one of them responds differently to the temperature change, then they will be debonded from each other and act separately, and our structure will fail. Luckily, steel and concrete have almost a similar coefficient of thermal expansion. By the way, the field of using other metals in reinforced concrete is an active area of research. For example, in seismic areas in California and other states, researchers are trying to use memory alloys that deforms well during an earthquake, but then goes back to almost the initial shape without excessive permanent deformations. Anyways, this was just a bonus. Let's go back to regular reinforced concrete. If you are interested to learn how to design your house using reinforced concrete or pursue a career in structural engineering, then let me tell you more information about that. When you start learning about reinforced concrete, there are several assumptions made. Even though we said concrete has little bit of tensile strength, we actually assume it's negligible, just to be safe and make the design process easier. We also use safety factors and load combinations in our design to make our design safer. We also want the steel to yield first. Remember, steel is ductile, while concrete is brittle. In other words, steel will elongate plastically like a gum before failing. This will give the engineers a sign to ask the residents to it falls. However, if concrete fails before steel, then we will have no sign before failing, and you will be sued most probably. And concrete stress profile in the structure looks a little bit weird, so we will assume some stuff before we begin the design. So this video was a short overview of reinforced concrete. So let me know what you think. Thanks for watching and peace.
Welcome to the session Fibre Reinforced Concrete, FRC. Myself, Mr. Chetanji Kunapre, Assistant Professor, Department of Civil Engineering, Palchan Institute of Technology, Solapur. Now these are the learning outcomes. At the end of this session, students will be able to understand the features of fibre reinforced concrete and factors affecting properties of fibre reinforced concrete. Now, as we know, the concrete is a mixture of basic ingredients, cement, sand, coarse aggregate, and fibre reinforced concrete means some addition is made in that concrete. So we can define this concrete as it is a mixture of cement mortar or cement concrete with discontinuous, discrete, uniformly or orderly or randomly dispersed fibers. So that is fibre reinforced concrete. Now, what is the need of this type of concrete? Now, our plain concrete actually it possesses very low tensile strength. So low tensile strength means if any tensile stresses are occurring in the concrete, probably that will be subjected to the cracks. Now these cracks will widen, and the reason for low tensile strength is the micro cracks. And micro cracks and presence of micro cracks and their propagation will reduce the tensile strength. Now, how this tensile strength of concrete can be improved? One is the conventional method. Conventional reinforcement or reinforcing bars can be introduced in the concrete. So that is our regular RCC. And second is tensile strength can be improved by introducing the tendons into the concrete, and that is pre-stressed concrete. But these are improvement techniques to improve the tensile strength of section, not of the concrete. So concrete will remain as it is, which is brittle in nature. Now, before loading, concrete is subjected to cracks, micro cracks. The reason is the drying shrinkage. Because of drying shrinkage, there will be micro cracks, and whenever these micro cracks are subjected to the loading, these cracks will open up and start to propagate also. One more important thing is initially the width of these micro cracks will be very small or with a few microns also. But the other two dimension, depth and width of these cracks will be of higher magnitude. So in case of structural cracks, these are proceeding or they will proceed slowly. So the crack is a major problem in our regular concrete. Now we need some crack arrestor for which is the disadvantage of the plain cement concrete. So addition of some fibers which are small, closely spaced, discontinuous and uniformly dispersed into the concrete will act as a crack arrestor. So functioning of crack arrestor that is done by these fibers. So continuous meshes, woven fabrics and long wires are not fibers. So discrete fibers which are dispersed in the concrete, these are called as fibers, and that concrete is called as fiber reinforced concrete. Now, which properties of concrete will enhance by these fibers? We are talking about tensile strength, but what are the other properties which will enhance by fibers? You pause the video and think of that and write down the other properties which will enhance by these fibers. Now, following properties of concrete will enhance. First is the flexural strength, bending strength of the concrete. Second, impact resistance of the concrete. So surface of the concrete must be very tough. Crack resistance of the concrete. So cracks shall not propagate or will not propagate because of the fibers. Toughness of the concrete, and more important property is ductility of concrete, that will enhance. The concrete is brittle in nature, so by addition of the fiber, if the ductile property of the concrete increase, that is the better advantage. Now, there are various fibers, and these different types of fibers can be used, but all that cannot be effective and economic also. But each fiber has got its own characteristics and limitation. So let us see the fibers. Now, steel fibers, polypropylene fibers, nylon fibers, asbestos, wire, glass, and carbon. These are the different fibers used in the concrete. Now, what is this fiber? Fiber is a small reinforcing material. The shape of the fiber may be circular, flat, with the straight end, with the different end, with some texture or crimped surfaces. Now, this fiber can be described with the aspect ratio. Now, the aspect ratio of the fiber is the ratio of its length to its diameter. Now, typical aspect ratio of the fiber is ranging from 30 to 150. Generally, it is kept 120. Now, these are the steel fibers. You can observe these steel fibers, and at the end, the ends are hooked, and this will act as anchorage into the concrete. So, round fibers and hooked fibers, in both types, the steel fiber is available. Diameter is 0.25 to 75 mm. Now, it improves the flexural, impact, and fatigue strength of the concrete. Now, application of the steel fiber is in the overlays of the roads, airfield pavements, industrial floors, and in some.
Since its introduction over 40 years ago, steel fiber reinforcement has proven its merits in the most demanding structures and applications. The core difference between steel fiber and other reinforcement solutions is that fibers are part of the concrete matrix, turning it into a composite material. Instead of providing strength in distinct locations, steel fibers form a reinforcing network throughout the entire concrete structure, increasing its overall ductility. So how does this translate into concrete behavior? Take a random concrete structure. When subjected to loading, compressive and tension stresses start to build. Over time, small cracks will appear in places where the stress reaches a critical point. Steel fiber interacts within the concrete matrix, absorbing tensile stresses at any point and in any direction. As a result, steel fiber picks up small cracks much faster than traditional reinforcement. When a crack occurs, the hooked ends of the fibers remain solidly anchored on each side of the crack, acting as a stress transfer media. Once the maximum bond strength with the concrete is reached, the pull-out takes full effect. This enables the next fiber to take over, delaying cracks from growing. Different loads require different steel fibers. To meet any design requirement, Beckart offers 3 steel fiber types: Dramix 3D, 4D, and 5D. Each fiber has a different hook, strength, and ductility. Consequently, they also behave slightly differently when dealing with stresses. Let's take a closer look. First up is Dramix 3D. When a small crack occurs, the 3D hooks firmly anchor inside the concrete matrix. As the stress increases, the hook slowly deforms. As soon as the fiber loses its bond with the concrete, the pull-out takes full effect. Dramix 4D provides the same process, but with even better anchorage and a significantly higher tensile strength of 1,650 Newton square millimeters or more. Dramix 5D behaves differently altogether. Here, the hooks never pull out from the concrete. As the stress increases, the wire slowly elongates until it reaches its maximum strength. With a tensile strength of 2,300 Newton square millimeters and elongation of 6%, concrete structures reinforced with 5D can take high flexural stresses over a long period. Based on these behaviors, we can conclude that Dramix steel fibers effectively increase the load-bearing capacity of concrete. It can be used in almost any concrete structure with or without additional reinforcement, where the ductility of your concrete structure depends on the length-diameter ratio of the fibers and the number of fibers used per cubic meter. It is essential that enough fibers overlap to create a continuous network in the concrete mix.
Next is polypropylene fiber and nylon fiber. Now this is polypropylene fiber. So it has got very high tensile strength, but the modulus of elasticity E is very low in case of polypropylene fiber. But because of the elongation, because its modulus of elasticity is less, definitely there will be higher elongation and it will not contribute to the flexural strength. Now next is asbestos. This is mineral fiber. Tensile strength is 560 to 980 Newton per mm square. So it has got high flexural strength than cement paste. Now next is coir fiber, jute fiber. So this is a coconut tree. You can observe these fibers here, and one is the cross section, longitudinal cross section of this fiber. So coir fiber is in this form, which is a natural fiber that can be used in the concrete where that much tensile strength is not expected. A little bit improvement is expected by using the coir fiber. Next is glass fibers. This is a recent introduction into the fiber reinforced concrete. Tensile strength of glass fiber is 1020 to 4080 Newton per mm square. But glass fiber is affected by alkaline conditions. So alkali free or alkali resistant fibers are important, so that can be used in concrete. So one trade name is there, that is Senfil, which is alkali resistant glass fiber. Next is carbon fiber. Now tensile strength of carbon fiber is 2110 to 2850 Newton per mm square. These are used basically in cladding, panels and shells or type structure. So their use is started yet now. The mass scale, if it is used, definitely that will be one of the promising future. Now these are the factors which affects the properties of the FRC. Because whenever some addition is made in the concrete, the properties may affect. Some property may enhance, some may reduce. Now by observing and studying the factors which affects the property of the concrete, we can give the best solution. Now FRC is actually mixture of fibers into the cement matrix. Cement matrix that which creates a better bond between cement paste and the aggregate. Now first factor is the fibers may be orderly manner or randomly distributed. This is the first factor. If proper distribution is there, definitely the properties of FRC will increase. Second thing, important factor is transfer of stresses between matrix and the fiber. Whatever load or stresses are coming on the concrete, if all these stresses are effectively transferred from matrix to the fiber, then definitely your properties will enhance. Now what are the factors, sub-factors which will affect the transfer of stresses? First is type of fiber. Second, geometry of fiber, whether it is a plain fiber, crane fiber or hooked fiber. At the ends, what is the geometry, that is also important. Third is fiber content. So percentage of the fiber is important. So fiber content is the third sub-parameter. Fourth is orientation and distribution of the fibers. If it is distributed properly, if the fiber orientation is perpendicular to the crack, definitely that will arrest the crack more effectively. And next is size and shape of the aggregate. Fifth point, which is important point, because based on the size and shape, the cement matrix and its arrangement is dependent. And sixth is mixing and compaction technique of the concrete. So how the bond will develop into cement matrix and fiber, that depends upon this compaction. Now next is for efficient trains transfer. This is important factor. For that, Young's modulus of matrix must be much lower than the Young's modulus of fiber. This is important factor. Next is the bond between fiber and the mix. Now you can see this diagram. This beam, which is a flexural member, so load is applied. Here one crack is developed, and this is the fiber mesh. So this crack is arrested by the fiber. Now how it is effective? So the bond between fiber and mix, that actually plays important role in the stress transfers. How the stress is transferred to each other, that is dependent upon interfacial bond. Okay. And last thing is the improvement in bond of the fiber and mix, that depends upon the larger area of the contact. So this larger area of the contact means the bond will increase by the area of contact between fiber and matrix, and if it is improved, then the frictional resistance and the degree of gripping, that will improve. And one more aspect is there, we can increase the bond by sodium hydroxide.